Yeah, now it's okay. It's now full screen.
Okay, guys, I will just get started. First, thanks for the nice introduction, and also for the first time to see everyone in this conference for the first time. And also, I'd like to thank the organizers for inviting me to giving me this opportunity to talk at this wonderful conference. So I will be talking about something like ensemble average of different theories, and especially I'm going to focus on the relations between ensemble average of truly random theories and some pseudo-random theories that emerging from treating a large number of microstates. So the talk is based on this preprint. And okay, as we have all learned, and partly from this wonderful conference, that there has been quite a lot of breakthroughs in recent years that deepens our understanding of classical GR and especially the gravitational path integral. So if we want to summarize, if we dare to summarize all these recent advances in one sentence, I will choose the following, that is, the gravitational path integral is actually computes quantities that is in the ensemble average of different theories. Now, for example, the simplest example is the case of Jacobi tidal gravity, which is shown to be due to an ensemble average of random matrices. And to provide some more backgrounds, I guess I can start with this paper that, in my mind, is the first paper that kicks off the whole recent development. That is this paper by Seth, Shanker, and Stanford. What they were doing is to take a close analysis of this spectral two-point function computed in the SYK model, but from a gravitational point of view. So just remind you that the SYK model features a random coupling J. So what you can do to compute this two-point function is to first fix the random coupling to be one value and compute this one maybe numerically like what is shown in this figure. Oh, by the way, can you see my mouse? Can you see the pointer here?
Yes.
Okay, great. So yeah, if you do the numerics like that, what you'll get is this red curve that will be like this. There will be a lot of oscillations. And then what you can do is to change the coupling a little bit by, but still from the same Gaussian distribution. This is like you prepare the system for a different time. And then because the coupling is random, it will change, but it's from the same random ensemble. And then you will get different red curves. And what you want to do is then to average over all these, maybe you can try maybe 100 or 1,000 times, and you want to take an average of all these trials. And the result will be something like this black curve, which has basically 3 linear regions. One is called the slope, and following by the ramp. And finally, there will be a plateau. So what these people have done is to successfully reproduce the ramp area in the gravitational path integral computation by including a new topology, which is these basically 2 boundaries that is connected by the interior. You have 2 boundaries because you are computing the two-point function. But the new ingredients is that you have to include this kind of topology. With this, you reproduce the ramp. And then in some follow-up papers, they have shown successfully that if you include more and more different topologies, there will be there will be enough to contribution from in the gravitational path integral to reproduce the plateau area as well. So this, as you can see, is an explicit example showing that the gravitational path integral actually computes the ensemble average of some quantity. Well, there has been a lot of other examples. For example, there will be this parallel but still very seminal work by Maroff and Maxfield. So what they have shown is that you can try to compute in the context of holography, compute the correlation function of some partition functions on different boundaries. And the way they compute this one is through by holography through the gravitational path integral. And what they compute is, for example, in this two-point function case, you have 2 boundaries, there will be some 2z insertions. And from the gravity point of view, this correlation function is nothing but a sum of different geometries in the bulk that can fill in the regions in between the boundaries. So because they considered a trivial, sort of not trivial, but it's a simple topological gravity theory. So this gravitational path integral turns out to be, can be done exactly by summing over different topologies with some weight, which is simply a topological gravity action. And their result is very simple. You can be rearranged into this form. For example, this is for the case of arbitrary n. So basically, the interpretation of this result is that if you consider the endpoint correlation function of the boundary partition functions, it can be, the gravitational path integral gives a result that can be rearranged into a sort of an infinite sum of integers runs from 0 to infinity, d to the n multiplied by a weight factor, which takes the form of precisely the mass function of Poisson distribution. So now you can interpret the result, because here you have d to the n, which is the same as z to the n. So the d can be identified with the expectation value of each single z. And because the theory is topological, the expectation value of z is nothing but the dimension of the Hilbert space. So basically you can see that the sum over d from 0 to infinity is actually a sum of different theories with different dimensions of Hilbert space. And again, due to this weight factor, this is not merely a sum, it's actually an average, which is like you have a random, it's like you have a random variable d, and the d is drawn from a Poisson distribution. So in that sense, you can reinterpret the result as the gravitational path integral, which computes this one, is actually computing an ensemble average of different theories on the boundary. So this will be a different example, which again explicitly demonstrate how this slogan works. And also there are many other, okay, not that many, but still there are many other papers or interesting papers discussing, like also in this direction, the relation between gravitational path integral and ensemble averages. And all of those are great and are very interesting and very illustrative. While facing all these fascinating results, there are some questions indeed in the community. And basically, those questions are all about the nature of these ensemble. Well, these questions are actually very natural because typically these ensemble average of random theories are not what we learn from the textbooks. So we all know how to quantize a theory with a Hamiltonian or with an action by doing, let's say, path integral or canonical quantization. However, if you imagine you were given a set of different theories and you were asked to quantize the average of this set of random theories, at least myself, I don't know how to proceed immediately. So then, so this is basically the question, how to understand like this ensemble average. And there has been a lot of thoughts on how to answer this question in the community. And I think among all of those, there is one particular proposal which is very appealing to me. That is to say that, okay, what you are computing is not really an ensemble average of truly random theories. What you are actually computing is only over some pseudo-random variables that emerges from your treatment, like from co-screening or just ignoring some microscopic structure from in a maybe parent microscopic theory. And then basically what that means is that when you co-screen a little bit of your microscopic theory, there will be some pseudo-randomness emerging. And if you focus on this pseudo-randomness, there will be like some pseudo-random theories that you want to average. And the true random average over the theories is really an analog of those pseudo-random theories. So from what I present these questions and the proposal, you can see already that I'm going to take this pseudo-randomness more seriously. Well, I'm going to take the true randomness so seriously. And another reason of my stand is that this pseudo-randomness, as I just briefly explained, is a emergent phenomenon, which is very similar to gravity. So there is a hope deeply in my mind that there might be some relation between this emergent pseudo-randomness and gravity. which hopefully we can see the connection later.
But sorry, can I ask? But
Sure.
where is the? What is really the origin of that pseudo randomness? Because from RG, we know you could have different UV, but commonly you flow to the same infrared.
Yes.
Here
so
something
right.
inverse.
Yes. So yeah, actually that's a good question, which I hope to come to more details in the later example. But roughly speaking, the simple explanation is that when you deal with a large number of microstates, there's no way to handle them one by one. You have to do some like clustering of of them into small subcells, and then using some statistical or quantum statistical methods to deal with that. And then when you have that, when there's a statistical property, there is some pseudo-random variable emerging. It's like the previous Marov and Maxfield example where you have this D, which is not really a random variable, but because you have these distributions, it looks like a random variable. It can be interpreted as a random variable. And I will talk about this in detail in one later example. So maybe we can see if that's clear from that example.
Okay.
Is it okay?
Yes.
Okay. Yeah, thank you. Right. So basically, our goal for today is to first take the first step in understanding all these proposals by looking for some concrete models that first realize explicitly those ideas, maybe vague ideas, and try to set up a stage on which hopefully some more in-depth study can be done to further understand what is the real reason why this ensemble average makes sense. And to achieve this goal, we are going to take the following strategy. We are going to start from some simple models with true randomness, and then we will try to find out the microscopic parent theory that could have some pseudo randomness emerging after we do some cross screening or we ignore some microscopic degree of freedom. Hopefully, these can become clearer in the later example. And then we will show that this pseudo randomness is actually an analog, or the other way, the true randomness is an analog of the pseudo randomness. And hopefully we can connect the different random theories with gravity. So that's the plan for today. And okay, all these sentences can be summarized in this picture, which, okay, don't take it wrong. It doesn't mean all this business is a piece of cake. It just means that there will be 3 different layers of the story. So there will be the top layer that is the true randomness that we are familiar with. And then there will be a bottom layer which contains some microscopic parent theory, which is underlying. So this will be the thing that we are going to pursue. And by doing this cross screening, there will be a middle layer. There will be an emergent pseudo randomness that's bridging the true randomness and the single theory. That you don't have to, you can only average over microstate instead of averaging over theories. So let's go to some details. So first we will try to construct a truly random theory. So previously there has been a lot of discussions as you briefly in the introduction. All of the previous discussions, or most of the all, about continuous Gaussian distributions. Well, this is very sensitive. This is very sensible because this is a simple distribution and people know how to do Gaussian integrals. So it's simple, it's well studied, and also is in good control. But because today we have this microscopic origin in mind, we would, and also because we have these, we know that the quantum theories all have discrete Hilbert spaces. So with this in mind, we should consider some discrete distributions where the random variables can take discrete value. And in addition, there has already been explicit examples in the literature showing that discrete distributions are actually relevant in the gravitational path integral. This is again the example of Marov and Maxfield, where they have shown that if you do gravitational path integral, the sum can be, the result can be rearranged into a discrete, a average over some theories subject to the Poisson distribution, which is probably the simplest example of discrete distributions. Yeah, and also we will show that this Poisson distribution, this discrete distribution will be also under good control, so we can do some detailed analysis of it. And the precise, the explicit example we are going to consider will be simply a scalar theory, where we will turn on some sources, and the source, and the second will be a random source that will be related to the random distribution so far. And our goal first is to try to integrate out or average over the random source to get an effective action using sort of this prescription. Well, immediately there will be two questions we have to deal with. First is that what set of theories would you like to put together as a set to be averaged? And second, what measure should you use to do the average? Well, this is actually two general questions for all the other like discussions of ensemble averages. Like we have to always determine, this is a general question, and I think, and as far as I know, by now there has not been yet a universal sort of standard or criteria of how to answer these two questions. So up to now, it's all worked out case by case. So we will still facing the same questions, and we will just give an answer that is suitable to our specific model. So basically, there will be some trial and error. So after some failures, it turns out that a sensible choice for this set of theories and also for the probability for the integration measure to use is the following. So suppose you have you define your theory on some background as perhaps R to the D, and then we can consider a discretization of the space-time of the M into small cells or small volume elements. And then basically what you want to choose, the theory you want to choose are those whose sources or actually the fluxes of the source, the J1 times dV, which is the flux of the source, goes through each of the sort of small cells, are discretized. And this discrete value should satisfy some Poisson distribution with some Poisson parameter like this. And then further, you want to assume that the distribution, the Poisson distribution on each side, on each cell, which is labeled by N, is mutually different from each other, the distributions from other unit cells, so that you can take a product over all the cells that you do in your discretization. And in each factor will be a Poisson distribution. And well, immediately you see there are some unusual features of this distribution, of this integration measure. First, it's like it's local in the sense that the distribution depends on position, which is quite different from the SYK model, where the random coupling is just a constant. There's no space. There's no X dependence. And secondly, you see that the thing that falls into this Poisson distribution is not really the source. It's actually the fluxes of the source. So the volume elements also entered the distribution, which is again different from the SYK model. And so in that way, we should really think of some fluxes that's really quantized and obey the discrete distribution rather than the sources themselves. So basically with this a little bit unusual feature, maybe I should try to visualize this a little bit by giving different colors on the different cells. So basically the different colors representing different fluxes, and the more bluish the color is, the smaller this value of fluxes, which is bounded from below by 0. And the reddish the color, the larger this flux is. So basically the figure here will be one configurations, or say one choice of the source or one choice of the action you want to average. And then your goal is to average over such theories with this integration measure of the sources. And also this lambda appearing in the Poisson parameters, they will determine the shape of your sort of randomness of your theory. And now with all this, with this p, and then we can just carry out this integral to get the effective action. We can just plug in the expression for the p's and to compute the average, the average of the random source that we introduce in the action. And the result will be something like this, which you can see is a, well, if you put back all the kinetic terms that were already there, which doesn't enter into the ensemble average, you just get this action, which is very similar to a Liouville theory. And the only generalization is that here, this parameter is not a constant, but actually depends on position. We can make this parameter a constant, but for generality, I will just keep this as it is. It's a general function. Well, if you are familiar with Liouville theory, you realize immediately that the sign here is actually not the correct one. The potential is not really bounded from below for this sign. So to cure this, you have to, modify your integration measure a little bit by including a small twist factor -1 to the f, which is defined here. So basically with this new measure, you can average over different theories to get a new effective action, which is now with the correct sign. So, okay, up to now, maybe you might think this is a little bit unusual and a little bit hand-wavy. It's not the things that you are familiar with. So you may ask, is there any like more accurate description of what we have done just now? And actually there is. So there is actually a mathematical description in terms of so a Poisson process is, the definition of it is a little bit boring. It's a random countable subset pi on a given carrier space. Now we can just consider this carrier space. And the Poisson process should satisfy two relations. One is that for different subsets on our R to the D, you can define random variables, which is this n of A that counts the number of intersection between the subset pi, the Poisson process pi, and the subset A. So on each of AI, you can define a random variable. And this n should be mutually independent from each other. And secondly, the random variable n on each side, on each subset should satisfy the Poisson distribution like this, where the lambda is the Poisson parameter, where well, in this case, in the terminology of Poisson process, is called the mean measure. And in all the cases we are interested in, we will consider the cases where the mean measure is determined from an intensity function, little lambda, from this little integral. So, okay, this is supposed to be a joke for Chinese, but okay, let's cover it up. To illustrate what is the meaning of this Poisson process, we can use this figure. So basically all the blue dots here, the collection of those will be the Poisson process. Basically, the background triangulation will be the set of subsets AI that we choose on the M. And the random variable n will be just to count how many blue points are there in each cell. So basically, the Poisson process just tells you that, okay, this number on each cell will be mutually independent and they fall into Poisson distributions. Well, if you have this in mind, and if you still remember what we had previously in the flux interpretation, you find this is nothing but the fluxes that we were talking about, where the flux or the color is now interpreted as the sort of the intersection number, the number of how many points are there on each cell. So then we can rephrase all the previous computations we have done in terms of this Poisson process, where now these random sources is now, as I just briefly explained, is now interpreted as the random variable, which has another name called random counting measure. It's a measure because it maps a subset into a number. It's a counting measure because it's defined to be the intersection number. So it takes integer numbers and it just counts how many intersections are there. It's random because we assume this person process assumes this value to be a random variable. So it's a random counting measure. And then we can now choose this subset to be infinitesimal, so that the integration integral here is a little bit immaterial. So you can just drop it and write for infinitesimal volume, the random measure is just this quantity. And using this, we can rewrite our the term in our action, this random source term in our action, in this way, which is there's no contact, it's just a trivial rewriting. And then averaging over the random sources in our physical setting is now translated into nothing but this Laplace functional in the post-process language, where fortunately we know how to compute the Laplace functional of any test function in a post-process, and the result will be like this. So now we plug in our expression, and we just get this output as a result. But then you find this is nothing but the previous result that we got from our previous more physical derivation. And again, there will be a factor of minus sign, but this can again be accompanied, corrected by this -1 to the MB factor in the integration measure. So let's do a quick summary of what we have done now. So essentially what we have done here is in roughly parallel with the SYK example, where you start from the SYK model that had some random couplings inside, and you want to average over the random coupling to get an effective action in terms of the G sigma, the bilocal fields. And then you can take further some Schwarzen limit to get a Schwarzen effective action, which is shown to be due to JT gravity. Now, what we are doing is a simple model with only some random sources, and we average over these random potentials or random sources, and then we will land on something that looks like a Liouville gravity. So this is in parallel to the SYK. And along the way, what we have shown is that we have determined which set of theories to be averaged over. This is the set of theories whose fluxes is discretized. The fluxes take integers, but not the sources. Recall that in the SYK, it's really the coupling constant. That's really from a Gaussian distribution. But here, we don't assume the source, but actually we have to have these fluxes. And secondly, we have also demonstrated how to choose the appropriate measure. And in particular, we show that you have to modify the very naive measure a little bit by this twist factor, so that your resulting theory is actually sensible in the conventional sense. So I guess here is the, we finished the first.
What is F? -1 to the F.
Yeah, sorry, I'm a little sloppy with notation. F is defined here. So it's again, it's a definition of, it's related to the source. Okay, the F is not really the fermion number, but it has a counterpart in the microscopic model, which is precisely the fermion number. So that's why I call this F. But it's probably here is not a good notation, only see this equation. Yeah.
Okay, thank you.
Yeah.
I have a question.
Sure.
Why you call this as a Poisson process?
Oh,
I did not see any time. Process normally means something changes time.
Right. Perfect. It's a good question. So this is something in the, I think in the applied math literature. So previously the Poisson process was first introduced in the one-dimensional case where you study like what is the pattern of a bus arriving at a bus stop. So this is a process just count how many bus stops in the time series. But now later people generalize the story into higher dimensions where there's not only a time direction, but also a spatial direction or more spatial directions. So they still use this notation of process where there is a time direction, but also there will be a spatial direction. You can treat this set of points so sort of dynamically as appearing one by one. So this is still a process. But indeed, in the higher dimensional cases, a more general, a more appropriate terminology is really, they call this a point field, which I guess is more confusing in our physical context. So I avoid using this point field notation and still call this Poisson process, which is also fun. In the math literature or in the math community, I think they just use Poisson process and point fields interchangeably.
Okay.
I'm just, yeah, the less worst case. Yeah.
Okay, thank you.
Yeah, thank you for the question. So let's go to the sort of the bottom layer of our cake, and this try to construct a microscopic model, which just a quick recap that we want to construct a microscopic model that could have some emerging pseudo randomness after we deal with the microscopic. Basically, what we are going to do is to first construct a microscopic model, and we want to go to a special double scaling limit to go to the infrared and get an effective low energy limit. And along the way, we will show that there will be some pseudo randomness appearing in the process, and we will hopefully demonstrate that this pseudo randomness appearing in the process is actually equivalent to what we have just saw from a ensemble average over true random theories. So this is the plan for our remaining of the talk, and concretely, we are going to start with a microscopic model which is defined by on a lattice, which is why we call it microscopic. So the lattice site is labeled by the position vector x, and on each side, I'm going to put a pair of fermions so that they will generate a two-level fermionic Hilbert space. And I'm also going to put the fermions on each of the lattice site. And the Hamiltonian of the system will be this, where basically it contains two pieces. One is the pure bosonic one, and the other one contains the coupling to the fermions. Now we want to prepare the system in a certain state that factorize between the boson fermion, the density matrix factorize between the boson fermion, and the fermion density matrix is actually a tensor product of the density matrix on each side, which is nothing but a mixed state with probability P on the excited state and probability 1 minus P on the ground state. So this will be a sort of a trivial microscopic model. Now we will do this sort of continuous limit. By this, I just mean you want to take the lattice spacing. A is the lattice spacing. So equivalently, A to 0 is the same as taking the number of sides. And then in this limit, you have, as n becomes larger and larger, there will be more and more sides. One sort of unit volume. Because you don't want the energy density to blow up, you have to take the following double scaling limit, where the P, which is the probability of being on the excited state, is going to 0, so that the product actually remains finite. So this finite quantity, we will give it a name, lambda little x. So this will be the double scaling limit that we are going to take. N goes to infinity while P goes to 0, and the product of the two remains a constant, or roughly order 1. So this figure shows how does this process look like. You can, by n goes to larger and larger, you are more and more coerced. So basically you squeeze more and more microscopic sites into one unit cell. But along the way of doing this, the total number of excitations, which is labeled by these orange little dots, they are roughly remains the same. So that's the idea of the limit. And now here, you can just do the cross-graining, which is where the pseudo-randomness emerges. So let's see how does this work. So let's see, because we are taking this large n limit, so there will be more and more states in your the size will be denser and denser. So basically, what we are going to do is the definition of the cross-graining. We are going to choose some small cluster of the lattice, which is denoted by the dV here. So dV is a small sort of a small cell, let's say, And we can now consider the density matrix of all the sites within this small cell. And this turns out, because the density matrix is just a tensor product, so in the small cell, it's again a tensor product of this. This is just by definition. And now we can, because we have a large number of those, there's no way to handle them one by one. What we are going to do is to rearrange all these microstates into the total number of excitations in the little cell. Because we are doing co-screening, the cell will be now the smallest unit we are going to discuss. So we just erase all the microscopic structure, just relabel them in terms of this case, which is a property of the cell. So K just tells you how many excitations are there in the cell. And then this is a trivial rewriting, and after you will get some coefficient in the rewriting, which just takes this trivial form. I mean, it's not trivial, but it's simple to derive. And now we can go to our double scaling limit, where we take the n to infinity, where the n prime, which is the number of sites in the little cell, also goes to infinity, while remaining the product of n and p, which is this quantity, to be finite. Well, it turns out in that limit, this coefficient approaches the Poisson distribution of the random variable of the variable k, with this Poisson parameter lambda, which is defined by the little lambda, which is nothing but this coefficient in this constant in the double scaling limit. So as you see here, this precisely demonstrates how this pseudo randomness appears. Previously, there's no randomness. You just have a lot of microstates. But if you do cross-screening, there will be some new labels, and the label fall into some distributions, and then you can consider this one as a pseudo random variable because you are averaging of this variable over some distribution. And now we can proceed to get some effective action of this phi field, which is nothing but tracing over the fermionic Hilbert space, where you have this rho factor and e to the minus beta h. This is more or less standard, but now you have to include this -1 to the f. You want to include this -1 to the f so that the trace over the fermionic Hilbert space is base independent. You can choose a different basis in the Hilbert space. To make sure that your result doesn't depend on this choice, you have to include this -1 to the f. So with this small, but again, this one is really the microscopic incarnation of the -f in the previous macroscopic derivation. So with this in mind, we can just plug in all the expressions previously we got to get the effective action using after you arrive at this effect. You can redefine some parameters to put this in the more standard notation, which you notice is again alluvial potential. And now what we are going to do is to further rewrite the classic, the kinetic term, the infrared limit of the kinetic terms, so that we can erase our memory of the fact that we started from lattice theory. So basically, this is more or less standard. We are going to use some more or less standard techniques in the condensed matter literature, where you just go to the Fourier space of the lattice. You pick out the lowest few Fourier modes to get a effective action of this low energy modes. And to simplify our computation, we are going to choose the hopping coupling to be only non-vanishing among nearest neighbors. So with this simplification, we can get an effective low energy effective theory looks like this, where there will be an emergent new sort of mass term for the phi, but it takes this in terms of the original parameters. But this, you can see, again, this is just a Hamiltonian for the Liouville theory. So basically what we have shown is that after this cross-screening process, there will be some effectively tracing over fermions. Microscopic states is the same as averaging over some pseudo-random variables, and you will get a sort of a similar Liouville potential as in the ensemble average of truly random theories. And actually, you can do slightly more as a double check of your result. You can try to first integrate out the phi field instead of tracing over the fermions to get a quantum mechanical model for the fermions, which there will be a new coupling for the fermion. So there will be an induced 4 fermion interaction, and the coupling will be due to integrating out the phi field from its kinetic term. And to the leading order of derivatives, which is the most relevant interaction you can have in this quantum mechanical model, the coupling will look like this. Well, the bottom line is that the allowed range of parameter to make sense of the story is m over t larger than 2. But you will see that there is actually a branch point. There is a discontinuity of this coupling when m equals to 2, m equals to 2t, which is on the border of this allowed range. But this is precisely when the effective mass of the phi field goes to 0. So this, well, then the pole here, or the branch cut here, is nothing but is really as what we would expect, because this is simply because we are integrating out a massless field at this point. So we are doomed to have a divergence in the coupling. So this just gives you a consistency check, but also it tells you that there's a due description of the theory in terms of a quantum mechanical model with a quartic charge coupling. It's not precisely SYK, but okay, it's similar. Now, the final comment I want to make is that previously I very briefly touched on this idea that there will be some probability measure, as you also have seen in the previous derivation, that there will be some probability measure emerging from either the microscopic treatment or the ensemble average of the true random theory. Well, there are some other measure emerging in the other emergent phenomena, the gravity. That is, there will be some volume measure in the fluctuating geometry, which is also a measure and is also emerging. So you would like to ask, is there any possible relation between these two measures? And recall that to see the direct connection, just recall the effective action we got from our previous analysis is just this Liouville theory. And if you compare this with the real Liouville gravity action in terms of the gravitational variables, you find the two actions can actually be identified if you do the following mapping between the variables on the two sides. Basically, you want to identify the variables in the gravity, like the metric or the background charge, with the sources and the distribution functions. And to make this comparison more manifest, we can go to a conformal gauge of the gravity, where the last equation trivializes immediately. And you find the second equation sets up a direct connection between the lambda, which appears in this distribution measure, and the e to the rho, which is this well factor, but also it is also the square root of h, which is the volume measure you want to use when you do this any GR integrals. So this already gives you the connection that we are looking for. And furthermore, there is one more relation, which is also interesting, so we can take a closer look at this equation. If we rewrite this equation in terms of only the field theory variables in terms of this classical source and the shape of the random sources, lambda, you find this equation tells you that the classical source J0 is really sourcing the log of lambda field, if this can be called a field. But just recall that the J0 was initially introduced as a classical source of the phi field. So the equation of motion of the phi should read like this: the J0 is the Laplacian of the phi itself. So now this equation simply put the log of lambda and phi on the more or less equal footing. And we can further recall that in the derivation of Liouville, the phi field is really the well transformation where the Liouville emerges as the response. So basically this phi and log lambda on the same footing is a further confirmation of our understanding that maybe you can consider this probability measure as some sort of has some gravitational meaning. And also the Q had some set up a scale which is also the scale of J naught, which characterizes the strength of the coupling. And further, from these equations, you see that all these gravity quantities, they only captures the average property of the microscopic. This lambda, recall, emerges from the cross graining. So it's the average of the microscopic structure. This is as what we would expect because gravity is emerging as the long wavelength limit of some UV degrees of freedom. But I think more interesting is that in our construction, we have some concrete microscopic configurations, which hopefully can be used to extract some useful information about the quantum aspect of gravity, which we all are looking for. So here's a brief summary of what we did, but given the short of time, I will just skip that. And I guess this is the last, actually this is the last thing that I want to say. I want to take this great opportunity and under the continuous encouragement of my colleague, I would like to make an advertisement of a upcoming winter school that we are trying to hold in late January next year in Dongguan. And we are trying to have some young, very young, excellent researchers in China to give in-person lectures about recent developments about these replica wormholes, quantum extremal surfaces, island formulas, and all of that. So everyone is encouraged and welcome to register for this winter school, including both students and postdocs and also faculties. Okay, that's really the end of my talk. Thank you for your patience.
Thank you. Any questions?
I have a question. You are considering Euclidean space-time?
Yes.
1 + 1.
Yes, okay, that's another good question. So, okay, first of all this discussion here is in the Euclidean signature. And secondly, the dimension of the discussion up to the very last example can be fairly general. So for example, this theory, I'm using the dV to represent the volume elements. I didn't write down the dimension because it can be, at least from this derivation, superficially, it works for arbitrary dimension. And including this mathematical interpretation, it also works in arbitrary dimension. So up to here, it's maybe also true in higher dimension. I didn't thought about this one very carefully, but superficially, there's no immediate obstruction. But the final, in this example, I'm more or less only focusing on 1 + 1 dimension. Yes.
Yeah, I have a question about the flux. What do you call a flux? Actually, it's normally understood as through some area, right?
Yes, yes.
So in higher dimensions, then
yeah,
it may maybe also some fluxes. I don't know. Yeah, but for Euclidean 2 dimensions, then I can understand it as a flux through the cells, right?
Right. Yeah. Right. Precisely. Yeah. Perhaps the flux is not the correct word to use. That's why I put a little quote unquote here. But I can't really look for a better word for it. And precisely, as you said, this is a generalization of the flux in the sense that there are both space and time. Also, it's in higher dimensions. So yeah, it's a little, yeah. That's also why I'm not fully satisfied with this description, so that I went to the math literature to see if there is a more rigorous way to derive it.
Okay.
Yeah. I also don't fully understand.
Yeah. Okay, thank you. I have another question about the appearance or emergence of the fermions in your formulas. So can I see that, yeah, from the microscopic origin, actually your fermionic number, I mean the sun, actually counts whether the number of points in a cell is odd or even. Is that right?
Yes, yes, yes. It's counting whether it's fermionic or bosonic.
Okay, then yeah. So I like to. So in certain sense, we may say, okay, what we call as points, counting of points. Each point there will be, if we view it as a fermion, then your F counts the fermion number or the fermion parity, right?
Yes, yes.
However, originally you have only phi. When you introduce psi, what's the relationship between the psi and that phi?
Okay, first let me check if my understanding of your question is correct. So you were asking like what's the relation between the phi and the
yeah. So first, yeah, what's your F in this formulation?
Oh yes, right. So basically the F. Sorry, yeah, I see. Sorry, I didn't actually define what is the F here. That's my bad. So basically the F is nothing but the NX here. So basically it just tells you that when you have one fermion excitation, it returns a 1. If you have 0 or 2, it returns a 0. So in all the computations, the F can be regarded as the NX, which is nothing but the product here. So I'm sort of changing. Yeah. I'm changing from the Fermi parity into the fermion number to make this computation.
Okay, but previously you have already introduced the -1 up to fermion parity, right?
Oh, you mean in the first part of the talk? There was right. So this.
My question is whether you have really realized this fermion parity into the model, or actually you put in the fermion by hand, then you identify this as well.
Yeah, so this factor actually also have the okay, that's a good question. I didn't go to. So actually this is also has the microscopic origin because we can see the expression of this guy, which is this one, right? And you can see that this is just -1 to this one. When the volume element is small enough, this is just a flux. And recall
no fermion here, right?
There is no fermion, but the flux, recall that in this interpretation, the flux is really the number, how many points are there in each cell. And now this point, if you go to the microscopic interpretation, the number of points here is the number of points of the number of sites on which the fermions are excited. So that number of points is precisely this number of points. And then this number of points is precisely related to how many fermions are there. And this fermion number is precisely the -1 to the F that goes to, sorry, I can't find that equation. Yeah, this equation is precisely this fermion number that you put in. So this is really.
Right. Yeah, here is okay. All right, okay.
Yeah, so there, okay. So from the truly random theory, that's a little bit, okay, that's another point of this work is to show that the rules you use to determine which theory to average and how to average can also have a microscopic origin, and it should be determined but not arbitrary. And here, this example hopefully will be one example to show that indeed that rules can also be determined. Yeah.
So my point here is that before your last model, actually, we do not need to start with fermions, right?
Right. Well, it depends on, yes, it depends on our taste of the result. If we don't have this -1 to the F, we will get with a minus sign here, which is again a legitimate theory, but there will be some instability inside.
I cannot hear you.
Oh. Hear me now? Sorry.
Have you finished? Yes. Yeah.
No. Sorry. Oh. Okay. Can you hear? So okay. Let me repeat. So I think your question is why we want to introduce the minus f factor in this derivation, and my understanding is that if you don't introduce that -1 to the f, the resulting effective action after the ensemble average will have a minus sign here,
right,
which tells you that the potential is not bounded from below. So it's still a valid theory, but there are some instabilities.
That's right.
Is -1 to the f. This is introduced so that your potential is bounded from below. So it has the correct sign. So then it's like, okay, you put this by hand, but you put it by hand to you make this choice of the integration measure so that the resulting theory is a more sensible theory. So I think you are right. This is in some sense by hand, but it depends on your taste. If we are like purist, we would like to insert this one to make sure the result is good, behaves good.
Okay. So my point here actually, I mean, what I'm concerned about is, whether this is a universal feature or not. Namely, somehow we need to introduce fermions into a theory so that the probability measure is correct, or quotation mark correct.
Yes. I think that's a very, very good point. That's I think that's also the immediate thought I would agree with. That if you believe there are some microscopic origin of everything, it's more natural to have fermions there. Yeah.
Okay, thank you.
Yeah, thank you for the good questions.
Any other questions?
Or I see there is a question in the chat.
Oh, yes.
But I guess probably I've already answered that in the previous questions, so it should be. Anyway, we can talk to each other after the talk. Yeah.
No further question. Let's thank Hongcheng again.
Okay, thank you.
Okay, and then thank all the speakers this morning. Very excellent talk.